Welcome back, High Performance Computing, Advanced Scientific Computing course. This is lecture 9, CFD and Parallel Computing. This is the outline of the course, which this year the course is specialized with the CFD, and lecture 9 it will be focused on the application of the parallel computing and the computational flight dynamic. In the beginning, we have a review of lecture 8, computational flight dynamic. We had a review on the background and history of the fluid dynamic, and there are three approaches in the fluid dynamic, which is experiment, analytical method, and numerical. Which is numerical is related to computational fluid dynamic, and during the development, the size of the project were growing, then it's required to have computing to solve the problem. Mostly when the CFD came into play, we discussed that the application, why we are using the CFD and how it's helping us. That means when we have domain of the problem in the fluid dynamic, with the CFD, we discretize the domain of the problem to small areas. We call them mesh or grid. And then with the algebraic equation, we're solving the problem according to its boundary condition for the meshes and for the grid, and then we're collecting all the solution for the domain, and then we have the solution for all the problem. This was the brief of the CFD approach, and we had a comparison of the experiment and analytical and numerical method and why we using the CFD. And then we had discussion about the computational cost when we have the large size of problem, when we have many meshes, when the computing getting too large, especially when the problem in the turbulence flow topic, and also when we have 3D solution, it's required to have a computing power, and this is where the HPCs come to play. Indeed, at this time, for most problem, we need to have access to high-performance computing to solve them. And on lecture 8 also, we had a short talk about the different method, which calls finite difference, finite volume, and finite element. We present the structure of the element and what is the advantage and disadvantage of them. We talk about the structure and unstructured method, and why we are using them, what the limit of the structured one. Also, shortly we talked about the boundary condition and why it's required in the problem. Indeed, for the CFD problem, the boundary condition is essential to be able to solve the problem, and depend on the boundary condition also we can have a different approach to solve the problem. Also, we presented a wide range of the CFD application which is available in the industry, in the medical studies, on the energy field, on the aircraft, on the car, and many other applications. So it's a broad area, and it's essential to be able to use the CFD, and also because of the requirement of the HPC, so we should be able to support the CFD with the HPC and solve the problem. This is the main key of the relevance between the CFD and the HPC. And in this lecture, we will talk a little bit in more detail what is the one of the biggest challenge in the fluid dynamic, which is turbulence flow, and we need the high performance computing. Outline of this lecture, we will have two parts. In the first part, we will talk about the parallel computing essential in the CFD. We will have some a short talk about the turbulent flow and what is the crucial matter on this area. Then we will have parallel architecture, which is related to CFD application in the turbulent flow area. We will present the topology of the parallel computing and what is the required parameter on the parallel programming for the CFD. Then in the second part, we will look on the setup of the parallel computing in the CFD, how we make the discretization on parallel computing, MPI in the CFD. We will have some example regarding the CFD method in the turbulent flow, RANS, LES, and DNS. We will make comparison of their cost and their performance to helping us how we choose the method according to the problem, and also about the HPC resources to solve the problem. So let's start the first part. Turbulent flow in the fluid dynamic area is currently the crucial issue, and still we can say based off the quote from scientists, it's unsolved problem. Indeed, in the fluid dynamic area, most of the flow it's turbulent flow. In the turbulent flow, the flow generated with some scale, or we call them coherent structure. They have different sizes, and depend of these sizes, it's required to be able understand the phenomena, and then using some CFD approach and solve it. According to the history, in 1922, Richardson, a scientist, he suggested the structure of the coherent in the turbulent flow, which means there is a energy cascade, which when the turbulent flow in the domain, it has a large scale and a small scale, and the energy from the large scale transferred to the small scale, and with these cascade, indeed the turbulent flow composed of the very large scale and small scale. Based on this idea, in 1935, also there is a statistic theory about the turbulent flow, because we don't have analytical solution for it. So Taylor in 1935, he proposed his approach in the statistical approach, and also in 1941, Kolmogorov hypothesis came to the turbulent flow to discover some more detail of this area. However, in the beginning, it was imagination. Maybe this hypothesis could cover all field of the turbulent flow, but shortly it's disappeared that the Kolmogorov hypothesis, which is called K41 in the literature, when you see it. The different is the hypothesis has some assumption regarding the homogeneous and isotropic of the eddies, which is only available on the small scale, not on the large scale. So these causes that these hypotheses of the Kolmogorov only be able to explain the behavior of the turbulent flow on the small structure, which we call them small eddies. then mm, there is not theoretical understanding of the turbulent flow for the large scale so far. That's why dealing with the turbulent flow is so complex. In this slide, you see some example. For example, there is a dye injection. You see when we will look on the dye trace, when it's laminar, it has a uniform structure, and when it's turbulent, has a very fluctuation and complex structure, and we are not able to predict it, for example. To specify the range of the turbulent flow, there is a non-dimensional number. It's called Reynolds number, which is defined by inertial force over the viscous forces. And these non-dimensional number used to specify the flow, it's in the turbulent regime or in the laminar regime. For example, when we're looking on the water in the pipe, in this range, Reynolds between 2300 and 4000, it's in the transition area. When it's 2300 and lower, it's laminar, and when it go upper than 4000, it will be turbulent flow. And also you see again when there is a different presentation when it's only laminar flow and when it's only turbulent flow. Also, the another example of the candle smoke plum. When we look on it, you see in the part of it has a laminar behavior and the other part has a turbulent behavior. So this is a different structure. When we look on the turbulent behavior, as you see on this smoke plum, in some part it has a small area and the other part has a large area. This is a different of the structure, which we call them coherent and also eddy. These different scale make the complexity of the turbulence flow. The Reynolds number, which is specify the range of the regime of the flow, which is turbulent or laminar, in different area has a different range. For example, when we talk about the internal flow in the pipe, you see in the circular pipes here the range laminar flow when it's lower than 2300, is turbulent flow when it's upper than 4000. And transitional flow, it's between these two number, which in this area the flow is not laminar and not turbulence, which is transition is happening. The another example here, you can see when we have a before the turbulence and after the turbulence. When we have a laminar flow before the turbulence, the particle they have a uniform structure. They are in the line. But when we have turbulence regime, they don't have a uniform structure, or they don't moving in any line, and they mix together here. This is a presentation of the flow in the pipe, which is internal flow, and we can see from the up to down how when it's laminar, when it's transition, and when it's turbulence has a different presentation. Regarding the flow, when we talk about the turbulent flow, indeed, because of the complexity, there is a fluctuation on the properties. One of the properties which most studies in the turbulence flow is the velocity. As you can see here on this figure, the mean velocity is a line, but we have many fluctuation, and it doesn't has any pattern to be able to predict it or find a analytical solution for it. That's why it's nonlinear phenomena. That's why the definition for the velocity in the turbulent flow is composed of the mean velocity plus the fluctuation. Also, when we talk about the boundary layer, when we have the laminar flow on the surface, the slope of the velocity has a different and it's larger, but for the turbulent flow also it's lower, and it has a different slope for these two different regimes. In this slide, we have a presentation of the boundary layer in turbulent flow. Of course, there are many details, and it's relevant to aerodynamic and fluid dynamic. But here we're presenting what is the difference on the turbulent flow and why it's important. For example, the boundary layer, one of this application when the flow passing an object, for example, when we have a sphere or a cylinder in the air or in the water, or one of the famous example that everyone experienced it, the aircraft when it's passing in the airflow. The flow when it's passing the surface, there are some specific condition which separation point is happening, and then it's have a critical adverse, which makes some difference between the pressure, and it's impacting the drag coefficient and drag force. For example, at this time, one of the open area of the research is studying the force on the wing of the aircraft. Indeed, the study, most of the study trying to reduce the drag force with the turbulent flow. We can say sometimes we like to have turbulent flow. When we have the turbulent flow, the separation point it's getting later. In this example, for example, you can see here a CFD simulation over a two-dimensional bond, which seems when the flow is passing it, when it's laminar and when it's turbulence. When the separation is happening too early, the difference pressure it will be too high, and then the drag force is too high. But when we make it possible to the separation point is happening later, we can reduce the drag force. In the turbulent flow, the drag force is happening later than the laminar one. The separation is happening later. So this is the some understanding of the boundary layer, and on the 3D object and in the turbulence flow. Since the turbulence flow we need to use the CFD, so when we are dealing with this issue we need the computing to be able to solve this type of the problem. And this example here is the CFD for the 2D, not for the 3D. This is also another example of the external flow. This is the same what we said about when the flow is passing the object. You can see many different application on the aircraft, on the energy, on the nature, and for example, development of the car. In the beginning of the industry of the automobile, indeed, because of the separation and the lift force, and also about the drag, the car has a different shape, but with the development, the shape of the car gets improved, and now we have these new cars. And you can see also every year we have different shapes, which they developing it based off the flow around the car to reduce the drag and especially reduce the lift of the car. You can see the drag coefficient and lift coefficient definition here, and you can see some example of the drag coefficient, how it's different between, for example, when the person walking and when on the bike, about the shape of the car, about the building, and also about the track. You can see the tree also, and this is the In the right hand side, there is a presentation of the experiment when there is a flat object, and when it's horizontal and when it's vertical, also about the sphere. And we can see the structure of the streamline of the flow when it's passing this area and what's happening. So this is one of the area. Of course, for the larger scale, it's very difficult to make experiment for them. So we need to use the computational fluid dynamic to solve this kind of a problem. And then in this slide, we have a presentation of the nature pattern, which is used in some design. For example, flow over a cylinder when it has a rotation, or when it's stationary, and it has a different separation or stagnation point, which make the lift on the cylinder. Also, it's similar with the in some kind same to the ball or the sphere when it's move on the flow in the air. For example, there is a Magnus effect. You can search about it, and you will be able to have a control of the track of the ball in the flow. Also, there is another example of the flap of the wing of the aircraft when it's activated and is making different effect of the lift of the aircraft. In the middle of the slide, you see example of the airfoil section, which one has a different angle of attack, and the stagnation point has a different location. It makes different lift force, and also it's about the drag, and you can have a control of the this section. The other example also in the right hand side, you can see when the military jets have the same pattern to a group of the flying. This is indeed from the nature, and it's helped to save the energy, because when they have this pattern, this shape, they're reducing the drag on their fly, and so they can save the energy. Indeed, this is a very interesting example from the nature, which is used in some design. After this, some example and visualization of the turbulent flow in the nature and the industry and many, we can say, daily application, let's have a look on the CFD, how helping us to deal with the turbulent flow. The first example from the Reynolds average Navier-Stokes models, which is approaching the CFD to solve a turbulent flow problem. In fact, in these models, the solution extracting the mean flow properties, we can say the average, and we don't have the exact solution. But because of the cost of the CFD in most other approach, like the large eddy simulation or direct numerical solution, so this is the great option to use it, and indeed we will be able to have mean flow properties in our design. For example, in some industrial application, firstly we need to study some aspect and then use it in the design. The RANS is a great option. But about the solution and about the detail, you can see here the presentation of the two examples. They use one of the well-known model of the RANS, K epsilon. We have different model. One of the well-known method is the K epsilon model, and it's used here. It's showing the right hand side. It's about the lift of the airfoil used to measure, and we can see the difference between the experiment and The advanced one, we can see the figure A has a proper match between the solution and it's we can say it's appropriate for the industrial application. In the in the figure B, we can see a little bit more difference between the advanced solution and the experience. So this is the capability and using the advance for this type of the problem. The other one is the example of the jet, for example, in the left hand side, the figure A is the for the jet example, and the another one for the wake. And we can see for the first one the difference between the experiment result and the advanced one. But in the second one, the match is proper and we can say has sufficient result to rely on this solution with advance. Then this is the presentation of the advance, and it's we can say it's the cheaper approach in the CFD for the turbulent flow. In the most study, it show it's 10 times cheaper than the LES, and 10 times is not something that we can ignore it, especially for the large problem. And then we can say it's one of the appropriate model we can use it to deal with turbulent flow. Then the another example of the CFD solution for the largest simulation is called LES. Indeed, in the LES, which based on its name, large eddy simulation, using some filter to remove and ignore some scale of the solution. Indeed, using the mean of the subgrid scale model. In this method, it's well known. And solving the problem, it's prepare much accuracy in its solution than the advanced, but it's much more expensive. When we have the 3D problem and we make a comparison between the advanced and LES, the computing cost has a difference, and it's very important to take decision you choose which one. However, we will see in some example in the second part, sometimes using advanced will miss some of the detail of the problem. For example, about the geometry. Then in some problem, it is required and we have to use LES instead of advanced to get the solution. But the main thing is we need to know the computing cost for this different method is different, and sometimes is effective to take a decision. And then in a turbulent flow calculation from the computational fluid dynamic, the most powerful approach is the direct numerical solution, DNS. Indeed, in this simulation, the mean flow and all turbulent velocity fluctuation calculated. It's able to solve on the special grid all the Kolmogorov length scale, and then it provides high accuracy of the solution, and we can say exact solution. But as you can see here, the statement is the calculation are highly costly in terms of the computing resources. So the method is not used for industrial flow computation. As we said before, we can see example of the DNS and how much is matched with the experiment, especially for high Reynolds number on the turbulence flow. Also, there are some statements regarding the benefits of the DNS, which is specified by Reynolds, Moyne. In this statement, for example, one of the interesting things is Reynolds noted that DNS has been used to calibrate hot wire and metric probe in near wall turbulence. So that means they're using it to this approach to set up their devices for the experiment. So that means it's providing detail like the experiment. However, because of the cost, it's limited in the application, and we cannot use the DNS for the regular or industrial application. So far, we talked about the different approaches of the models of the numerical in the turbulent flow. And when you look on the computing cost, we can see that this is the example of the cost of the DNS, which we need to calculate the grid points per dimension, which is especially focused on the small scale. The degree of the freedom, it's relevant to indeed Reynolds to 3, and this is make the computation to, especially when we have the 3D DNS simulation. However, usually the mean of the flow in many flow is repeatable and predictable. Then we can use the RANS solution. However, it's only about the mean or average of the flow. And as we said, 10 to 5 times RANS is cheaper than LES, so it's very important sometimes to use it. And we can see the length scale coverage by different approaches of the turbulence simulation. Indeed, for the RANS, it's only working on the large scale of the fluctuation. LES has a bigger range, which is covering the energy containing range. And when we look on the DNS, it's also cover the inertial subrange, and also it will be available in the universal equilibrium range. However, these DNS cover, it's according to the cost, we said it's very difficult to use it for the problem, and we need the required high performance computing resources to use it. Then the mostly advanced and LES use, and we can see the LES doesn't cover the universal equivalent range. Here is the short review on the parallel architecture in the HPC course. On the previous lectures, you had detail of these different configuration, which single interaction, single data, single interaction, multiple data, multiple interaction, multiple data. And also you saw the pipeline and vector architecture of the SIMD and the other structure. You saw how when it's a fully connected interaction network and some 3D hypercube, and they're playing different for the static interconnection networks when we talk about the distributed memory. Also, you are familiar with the shared memory currently, how it's used in the multiple instruction, multiple data, and distributed memory, which there is an interconnection in the network. And these different architecture is important when we are using the CFD and HPC to choose the right one and have a correct setup of the high-performance computing. Then, according to the parallel architecture that you know about it, we can have the topology definition now. Indeed, the topology define the way that the various processors are interconnected. Indeed, we need to know which processors are neighbor to each other, and we can use them. It has definite impact of the performance of the architecture because it's clear that neighbor communication is privileged in that the served via hardware. When we look on the topology, computer network is split into two broad categories, static and dynamic. For the static one, the connectivity pattern is fixed once and for all. But for the dynamic one, the support time changing connectivity pattern. We will see the different what method available for these different categories. So it's very important to know the topology application on the processor to make the performance uh, sufficient and get the good performance of the solution with the CFD on the hypervisor computing. Then about the popular static topology, there is a ring and one-dimensional tools, a mesh and two-dimensional tools, hypercube, 3 and fully connected. About the dynamic topology, there are many different, but there are most important topology are crossbar switch, bus, and multi-stage switch. And here you can see the presentation of these different one. For example, how the crossbar is working between the processor, the bus, the switch, and you can see the sixth category of the statics one. Regarding the static network, it should have a low number of the link per node. It makes it ideal network when we use the static topology. A small inter-node distance and also high number of the alternative path between any two nodes. Capability to increase the number of the node without changing the topology. To make the network cause the HPC application with a good performance, taking these some points, it make effective technique. And then this is about the topology which we could use on the CFD application with hypervisor computing. So after this short presentation of the parallel architecture and the topology which could be used in the CFD from the hypervisor computing, we can say the goal of the parallel computing on the CFD is reduce the elapsed time of the given application at a fixed size and solve increasingly large problem at a fixed cost in a time. And the third one, a summation of these two goals. Then we can understand what is the goal to using the parallel computing on the CFD problem. There are some main issues to controlling the parallel efficiency, a fraction of parallel content, load balance, communicativity, and redundancy, which they have much detail and of course in the some practical example we will look on these issues. Here the first part of the lecture 9 finished, and in the end there is a video from the YouTube which presenting the cloud cloud infrastructure for the CFD, I suggest you to watch this video, and we will back in the second part of the lecture to continue the talk about the public computing application in